Imagine a mysterious space rock barreling through our solar system. Uninvited, unknown, and unrepeatable. That's 3IATLAS, the third confirmed interstellar object to pay us a visit. It's like the universe's version of a tourist who doesn't need a return ticket. But what if this alien traveler suddenly split into thousands of fragments? Would we get a cosmic confetti show or a disaster movie in slow motion? Let's rewind for a moment. You know how a party sometimes gets that one unexpected guest who doesn't quite belong, the one who shows up wearing sunglasses indoors, speaks in riddles, and leaves before anyone can get their name. That's 3IATLAS. It drifted into our solar system out of nowhere, carrying the dust of distant stars on its surface. It didn't ask for permission to enter, didn't check in with NASA, and certainly didn't slow down for introductions. It just zipped by like, "Hey, love what you've done with the place," and kept going. Now, calling it a rock might be a bit of an understatement. This isn't some pebble skipping across cosmic water. It's a chunk of alien material that's been wandering through interstellar space for who knows how long. Billions of years, maybe. Long enough to forget where it came from. It could have been born near a dying star, tossed out like cosmic debris during the chaos of planetary formation, or launched by some ancient gravitational slingshot that said, "Good luck out there." Whatever the case, it's a relic of another world, a geological orphan drifting between suns. Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes, it's best enjoyed the way you'd enjoy a late-night conversation. Quietly, with a cup of tea, and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing. No pressure, only if you enjoy these calm journeys through the universe. Now, let's begin. When astronomers first spotted it, they realized almost immediately that it wasn't from around here. The trajectory gave it away. It was moving way too fast, slicing through the solar system like a hot knife through cosmic butter. Normal comets and asteroids dance politely around the sun in looping ellipses. 3IATLAS. It shot through on a hyperbolic path, the celestial equivalent of saying, "I'm just passing through. Don't mind me." And that's what makes interstellar objects like this so fascinating. They're not just visitors, they're messengers. Each one carries the fingerprint of a different star system. A unique mix of minerals and ices shaped by conditions we might never experience here. Think of it like cosmic archaeology, except instead of digging in the dirt, you're catching a flying rock that's been traveling for light years. It's the most extreme long-distance delivery service ever conceived. Now, let's talk about the part that keeps astronomers awake at night. What if 3IATLAS suddenly broke apart? Picture this scene. The object drifts a little too close to the sun. Its surface heats unevenly. Gases inside start to expand and then crack. It splits, not just into a couple of pieces, but into thousands. Suddenly, what was once a single alien traveler becomes a swarm of glittering debris, a cosmic explosion frozen in slow motion. From Earth, it would look both terrifying and beautiful. Thousands of fragments scattering across the void, each one catching sunlight and sparkling faintly like dust in a sunbeam. Except that dust is moving at tens of kilometers per second. The night sky might light up with faint trails, like an interstellar glitter bomb gone rogue. Astronomers would scramble to track the pieces, telescopes turning toward the same patch of sky, data streaming in, scientists muttering, "Oh no, not again," while also secretly thrilled. Because make no mistake, if 3IATLAS split apart, it would be the scientific opportunity of a lifetime. Every fragment would tell a story. Some might expose inner layers that have never seen light since the object formed, revealing alien ices or minerals. Others might vaporize completely, leaving behind spectral signatures, fingerprints of elements that don't match anything from our solar system. It would be like opening a cosmic piñata filled with clues about the chemistry of distant worlds. But of course, there's the small issue of where all those fragments go. In the vacuum of space, nothing stays neatly in one place. Each piece would follow its own path, influenced by the sun's gravity, radiation pressure, and maybe even a nudge from Jupiter's pull. Some fragments might continue on interstellar trajectories, escaping forever. Others could get trapped temporarily in solar orbits, looping around for centuries before fading away. A few might even wander near Earth's orbit, tiny, harmless meteors burning up in our atmosphere, giving us the rarest kind of shooting stars, ones that were born under another sun. There's something poetic about that. Imagine standing outside one night, watching a meteor streak across the sky, and realizing that the grain of dust you just saw came from another star system. It's like catching a postcard from across the galaxy, a cosmic wish you were here. Still, even as we imagine the spectacle, it's hard not to feel a bit of awe. Objects like 3IATLAS remind us just how connected the universe is. Space isn't an empty void. It's a bustling highway of wandering matter, where the leftovers of one system can end up passing through another. Every interstellar object that visits us is a reminder that the galaxy is alive with motion, chaos, and chance encounters. So yes, if 3IATLAS split into thousands of pieces, it would be dramatic. It would be dazzling. It would also be deeply humbling, a reminder that we're part of something much larger and much stranger than we can ever fully grasp. The cosmos doesn't care about borders or ownership. It just keeps moving, colliding, breaking apart, and starting again. And maybe that's the most fascinating part. Because while we stare up and wonder what might happen if an interstellar rock crumbles before our eyes, the universe just shrugs and says, "That's Tuesday. 3IATLAS isn't from around here. It entered our solar system at interstellar speeds, cruising too fast to be bound by the sun's gravity. It's a piece of another star system, a wandering messenger carrying the chemical whispers of a world we'll never see." Think of it as intergalactic mail that somehow landed in the wrong mailbox. To grasp how unusual that is, imagine standing in a quiet park and suddenly a baseball whizzes past your ear from nowhere. You didn't see who threw it. It doesn't match any ball you've ever seen. And before you can blink, it's gone. That's what discovering an interstellar object feels like to astronomers. Most comets and asteroids we track belong to our solar system's own backyard. Ancient leftovers from when planets were still forming. They follow predictable loops around the sun, like kids on a merry-go-round. But 3IATLAS? It came barreling through the gates, skipped the line, and didn't even slow down for a selfie. Its speed alone was a dead giveaway. Objects that belong to the sun's gravitational family travel at speeds that keep them tethered, maybe tens of kilometers per second. But 3IATLAS was cruising at more than 50 kilometers per second relative to the sun. That's fast enough to escape entirely. No return trip, no orbit, no chance of it ever becoming a regular visitor. It was just passing through, like a cosmic hitchhiker who took one wrong turn on the Milky Way. And the direction it came from? Nowhere particularly famous, not a known star system, not a recognizable cluster. That's what makes it both eerie and enchanting. It could have come from anywhere, the shattered remains of a planetary collision, the icy outskirts of a dying solar system, or maybe the gravitational slingshot of a binary star pair that yeeted it into interstellar space millions of years ago. Somewhere, long before Earth even had multicellular life. This rock might have been part of a world with its own moons, its own storms, its own dawns and sunsets, until gravity decided it was time to leave. Traveling between stars is no leisurely cruise. Interstellar space is a harsh desert, a near-empty vacuum scattered with stray atoms, cosmic radiation, and the occasional dust grain moving fast enough to punch holes in anything that dares cross its path. For 3IATLAS, to survive that journey, it must have been sturdy, but not invincible. Over countless millennia, its surface would have been sandblasted by cosmic rays, darkened by radiation, and reshaped by impacts so tiny yet so frequent that they'd leave invisible scars. Its surface might hold isotopic fingerprints, rare elements altered by deep space radiation that tell stories of where it's been and what it's endured. When it finally entered our solar system, it was as if a ghost from another galaxy had wandered into a city full of tourists. For astronomers, it was like spotting a celebrity sighting. Only this one didn't sign autographs or stick around for interviews. Telescopes around the world scrambled to track its movement, trying to understand what it was made of, where it was going, and, most importantly, where it came from. Every observation was a race against time. The faster it moved, the quicker it slipped from view. There's something profoundly humbling about that chase. We humans like to think we're pretty good at understanding our cosmic neighborhood. But every time something like 3IATLAS shows up, it's like the universe handing us a note that says, "You've seen nothing yet." For all our telescopes, sensors, and math, This object reminded us that space is full of wanderers, countless refugees from other stars that roam the galaxy unseen, each one a geological time capsule carrying the memory of worlds we'll never visit. And let's pause on that thought for a moment. This object is literally a piece of another solar system. Not metaphorically, not symbolically, literally. It was formed around another star, under different radiation, magnetic fields, and cosmic weather. The proportions of its elements, carbon, nitrogen, silicon, maybe even traces of frozen gases, are shaped by a chemistry alien to ours. If we could bottle even a fragment of it, we'd be holding material forged under a completely different sun. It's like finding a rock that proves another country exists, except the country is light years away and probably doesn't exist anymore. But perhaps the strangest thing about 3IATLAS is how ordinary it might have seemed at first glance. It probably looked like any other comet, maybe faintly greenish, with a misty tail of evaporating ice. Yet, behind that familiar disguise lies an entirely different origin story. It's a reminder that appearances in space can be deceiving. The same way two snowflakes look alike, but are never identical. Two comets may look the same through a telescope, yet one was born in the sun's nursery and the other in the unknown nursery of a distant, vanished star. Now imagine the cosmic odds that had to align for this rock to end up here. It had to be launched from its home system with just the right velocity, in just the right direction, and travel across unimaginable distances. Dodging collisions, navigating gravitational minefields, only to pass within our telescopic reach for a few short months. It's like tossing a pebble from one continent and having it land perfectly in a teacup on another. That's how improbable this encounter is. And yet, it happened. Somewhere out there, billions of other interstellar nomads are drifting silently between the stars, their paths as random and unknowable as cosmic poetry. 3IATLAS just happened to be one of the few that wandered close enough for us to notice. For a brief, shining moment, we got to watch it glide past, a ghostly messenger from another world. And then, as quickly as it arrived, it was gone again, fading back into the endless dark. If you could listen closely to its journey, if rocks could speak, maybe 3IATLAS would tell us about the star that once warmed it, or the planets it brushed past, or the long silence of deep space between suns. But perhaps that's the point. The mystery is the message. Its passing reminds us that the galaxy is vast, ancient, and full of travelers we may never meet again. And as it slips beyond our reach, 3IATLAS leaves us with a simple truth. In the grand cosmic ocean, we're all just strangers passing through the light. Before it starts breaking apart, let's understand what 3IATLAS probably is. Astronomers think it's a mix of rock, ice, and dust. A cosmic cocktail shaken, not stirred, by time and radiation. Its structure is fragile, like a snowball that's been sunbathing for millions of years. In space terms, it's one sneeze away from crumbling. When you picture an interstellar object, it's tempting to imagine something sleek and dramatic. A perfect metallic shard gliding through the void, glowing faintly like a spaceship from a sci-fi movie. But 3IATLAS is no interstellar supermodel. It's more like a cosmic clump, irregular, dusty, and possibly porous enough to make a sponge look dense. The universe doesn't care much for aesthetics. It builds things for endurance, not elegance. So, what exactly makes up this wandering mass? The current consensus is that 3IATLAS is likely a composite of frozen volatiles, materials that were once gases like carbon dioxide, ammonia, or methane, mixed with silicate rock and interstellar dust. Think of it as a frozen fruitcake that's been sitting in deep space since before Earth even existed. Every particle, every grain, is a record of chemistry that happened under completely alien conditions, perhaps near a young star surrounded by a disk of gas and debris. Inside, the structure would probably resemble something halfway between a comet and a rubble pile, not solid rock, but a loose agglomeration of pebbles, dust, and ice fused together over billions of years. This kind of formation happens when tiny bits of matter stick together in the earliest stages of a solar system's birth. Imagine microscopic dust grains gently colliding, electrostatically sticking, then merging into pebbles, which merge into boulders and eventually form larger objects. Most of those early creations end up as planets or moons, but a few are unlucky enough to be flung into interstellar exile. 3IATLAS was one of those outcasts, a planetary wannabe that never got the chance to call anywhere home. Its outer layers would have experienced the worst of space weathering. Without an atmosphere to shield it, every cosmic ray and ultraviolet photon that crossed its path would have chipped away at its molecules. Over time, the surface would darken and harden, creating what scientists call a mantle, a crust of carbon-rich compounds that act like cosmic sunscreen. It's not pretty, but it's effective. The mantle protects the delicate ices beneath from immediate vaporization when the object approaches a star. Under that dark shell might lie pockets of frozen gases, preserved for millions or even billions of years in perfect cosmic refrigeration. To put that in perspective, those ices might have formed when the universe itself was a younger, wilder place. Before humans, before dinosaurs, even before the sun. They could hold trapped gases that reveal the composition of the interstellar medium, the thin soup of atoms and molecules floating between stars from the time and place of their origin. That's like finding a sealed bottle of air from an ancient alien atmosphere, unopened since the dawn of time. But while its chemistry might be fascinating, its physics are downright unstable. A body like 3IATLAS isn't built for long-term durability once it gets near a star. The same loose, porous structure that helped it survive cosmic collisions makes it vulnerable to rapid disintegration. Imagine the difference between a rock and a snowball tossed into a campfire. One holds up, the other doesn't. As the sun's warmth begins to reach it, gases inside start to sublimate, meaning they turn straight from solid to vapor. This creates internal pressure, sometimes enough to make the whole object fracture or even explode. And it's not just heat that's dangerous. Rotation plays a role too. Many interstellar objects spin as they travel, some faster than expected. If 3IATLAS is rotating unevenly, centrifugal forces could tear it apart from the inside. Astronomers call this a rotational breakup, which is a scientific way of saying it literally spins itself to death. It's as if the universe built a self-destruct timer right into the physics. There's also the question of shape. We don't know exactly what 3IATLAS looks like, but if it's anything like its predecessor, the famous 1I Oumuamua, it could be oddly elongated, cigar-shaped, or even flat, like a pancake. These shapes are strange, but make sense for objects that have been battered by collisions and baked by countless suns over time. Each impact, each thermal cycle, slowly reshapes the body until it's more sculpture than sphere. If Michelangelo worked with frozen rock instead of marble, this is what his art would look like after a few billion years of erosion. What's perhaps most remarkable is how much information can be squeezed out of a single faint speck of light. Astronomers can't touch 3IATLAS or sample it directly, but they can read its spectrum, the unique barcode of light it reflects and emits. That spectrum tells us about its surface composition, the presence of organic molecules, and even the size of the dust grains it releases. Each observation adds a line to the biography of this traveler, helping us piece together where it might have formed and what kind of star once called it a neighbor. In some ways, studying 3IATLAS is like doing forensics on a rock that's been through a cosmic blender. You can only guess at the original ingredients based on the fragments left behind. But those fragments whisper stories of ancient heat, frozen chemistry, and violent ejection from a system that may have once had its own planets. 3IATLAS is both evidence and mystery, a reminder that not all worlds survive, yet even the wanderers carry meaning. So before we watch it crack apart and scatter, it's worth pausing to admire what it represents. It's a survivor of galactic chaos, a time capsule of alien chemistry, and a reminder that even the smallest, most fragile things can outlast entire worlds. Every atom in its crust is a witness to events that happened light years away and eons ago. 3IATLAS isn't just a rock, it's a relic of creation, drifting silently between stars, still holding the fingerprints of a sun that isn't ours. Now picture this. 3IATLAS drifts too close to the sun or gets smacked by thermal stress. The heat, the spin, and maybe a touch of gravitational tug-of-war pull it apart. Suddenly, it shatters, thousands of fragments exploding into space. It's like cosmic popcorn popping, except every kernel is moving at tens of kilometers per second. To truly understand the drama of that moment, you have to imagine the silence of space. No explosions echo, no booming sound effects like in movies, just light, heat, and motion. 3IATLAS, this quiet wanderer from another star, has spent eons in frozen peace, and then, all at once, everything changes. The calm becomes chaos. The sun's warmth seeps through its crust. The frozen gases inside awaken, and pressure begins to build in invisible chambers throughout its core. The rock groans, metaphorically, of course, as it faces forces it hasn't felt since it left its home system. Thermal stress is an unrelenting enemy. As 3IATLAS turns in space, one side bakes under intense sunlight, while the other chills in the cold darkness. The difference in temperature across its surface can reach hundreds of degrees. That might not sound like much compared to the sun's inferno, but for a body held together by fragile bonds of dust and ice, it's catastrophic. The heated side expands, the cold side contracts. Cracks begin to creep across its surface like fractures in glass. Each orbit of spin deepens the stress. The rock flexes, groans, and splinters until one of those tiny fissures finally becomes a fatal wound. Then comes the outgassing, the great cosmic exhale. Trapped pockets of volatile material deep within 3IATLAS suddenly sublimate, turning from solid ice directly into gas. That gas bursts outward, spraying jets of vapor and dust into space. Some of these jets act like miniature rocket engines, pushing the object and spinning it faster. Others shoot through cracks, widening them, breaking the already weakened structure apart. It's a runaway process. The faster it spins, the more cracks form. The more cracks form, the more gas escapes, and the faster it spins. The universe's most elegant feedback loop of destruction. When the final fracture happens, it's quick. One moment, you have a single interstellar traveler, battered but intact. The next, it becomes a cloud of debris, each fragment glinting faintly in sunlight. There's no explosion in the fiery Hollywood sense, but a sudden, silent cascade. It's the cosmic version of glass shattering in zero gravity, every piece floating outward in a graceful, deadly ballet. If you were watching through a telescope, the change would be subtle at first, a faint brightening as sunlight reflects off the newly exposed surfaces of fresh fragments. Then the brightness might fluctuate wildly as the pieces tumble and drift apart, each spinning with its own chaotic rhythm. Within hours or days, the once single speck of light becomes an elongated smear, a ghostly trail across the stars. It's humbling to think that such a delicate balance of forces could destroy something that survived interstellar space for millions of years. The sun doesn't even have to touch it. Just a little warmth, a little rotation, and the physics take care of the rest. In a way, 3IATLAS meets its end not through collision or violence, but through simple inevitability, an object built for darkness venturing too close to light. Now let's imagine the mechanics of the breakup in detail. Each fragment follows its own new orbit, dictated by the force of the breakup and the gravitational influence of the Sun. Some pieces will scatter outward, flung into wide trajectories that take them far into the outer solar system. Others will spiral inward, drawn towards the Sun's embrace. A few might briefly cross paths with planets, perhaps even Earth, before continuing their journeys into the void. The debris cloud becomes a vast, dynamic system of its own, a temporary constellation of shards tracing invisible curves through space. What makes this phenomenon so mesmerizing to scientists is how it can teach us about the physics of interstellar bodies. By tracking how the fragments spread, astronomers can infer details about the internal strength of the original object, how dense it was, how cohesive its structure. It's forensic science on a cosmic scale. The pattern of debris tells a story, whether it was a fragile clump of dust barely held together, or a denser, rock-like body with hidden veins of ice. Every piece of drifting debris becomes a data point, a clue to the mystery of its origin. But beyond the science, there's something profoundly emotional about imagining this moment. For billions of years, 3IATLAS wandered alone in the dark, untouched, unchanged, frozen in the deep cold between stars. It may have passed other systems, seen other suns, always surviving, always moving. And then, after an impossible journey, it finds itself undone by the very thing it never knew existed: warmth. It's almost poetic. The sun that illuminates our world is both the great giver and the great taker. The light that nurtures life but devours anything too fragile to face it. The breakup wouldn't just be a spectacle of physics. It would be a cosmic moment of transformation. The fragments of 3IATLAS wouldn't simply vanish. They'd spread out into new trajectories, reflecting sunlight in countless directions. From afar, they'd create a shimmering arc of dust and vapor, a temporary streak of brilliance against the void. For a brief time, this alien wanderer would paint the solar system with the light of another star, scattering the memory of its birthplace across millions of kilometers. Eventually, those fragments would drift too far to detect. The light would fade, the dust would disperse, and the name 3IATLAS would become another entry in the cosmic logbook of lost visitors. But that fleeting moment of its breakup, that burst of transformation, would mark the end of an unimaginable journey. It began as a frozen relic from another sun and ended as a glittering storm of dust near ours. And maybe that's how the universe writes its best stories. Not with permanence, but with change. 3IATLAS's destruction isn't just an ending. It's a final act of creation. In breaking apart, it reveals what it was made of, what forces shaped it, and what beauty lies inside even the most distant stranger. Like a cosmic chrysalis cracking open, its death lets us glimpse the hidden heart of another world, one that lived died, and finally, in a brief flash of sunlight, shared its truth with us before vanishing forever. Those fragments wouldn't just float peacefully, they'd spread into a vast debris cloud. Imagine a comet's tail, but multiplied by 1,000 and stretched across millions of kilometers. Each fragment could reflect sunlight, turning the night sky into a sparkling trail of alien dust. It would be the most beautiful mess the universe ever made. When 3IATLAS shatters, its story doesn't end. It transforms into an interstellar masterpiece of motion. Each piece, large or small, becomes a new traveler with its own unique trajectory. Together, they form a drifting swarm of dust and ice that fans out across the solar system like the aftermath of a silent cosmic firework. This is not chaos without elegance. It's the universe painting with debris, creating patterns too vast and fleeting for any human to witness in full. To grasp how extraordinary this event would be, picture a comet's tail, which is already one of nature's most exquisite displays. Now amplify that spectacle 1,000-fold. The debris cloud from 3IATLAS would stretch across millions of kilometers, a vast arc of alien material glinting under the sun's light. Each fragment, from boulder-sized chunks to dust grains finer than smoke, would catch sunlight differently. Larger pieces would glimmer faintly, like slow-moving stars, while the finer dust would scatter light into a soft, hazy glow. The result? A band of shimmering silver threading through the void, the cosmic equivalent of spilled glitter across black velvet. This shimmering field of debris wouldn't just be random chaos. The sun's radiation pressure, a constant stream of photons pushing outward, would gently nudge the smaller particles away, creating long, wispy tails that stretch in the opposite direction of the sun. The larger fragments, being heavier and less affected by light, would linger closer to the original path of 3IATLAS. Together, they'd form intricate patterns, overlapping streams, arcs, and spirals that evolve over time as gravitational forces twist and pull them apart. The beauty of it all lies not in permanence, but in its fleeting choreography. From Earth's perspective, this might produce a subtle but spectacular change in the night sky. For months, astronomers might track faint, glowing trails sweeping across constellations. Depending on the geometry of the fragments' orbits, some of this material could even cross Earth's path. If that happened, we'd witness something extraordinary: meteors made of interstellar dust. These would be shooting stars with no earthly ancestry, burning up in our atmosphere after journeying through the gulfs between stars. For a brief instant, pieces of another world would fall through our sky, their light winking out just as they meet ours. And yet, even as these fragments dazzle us, they also tell a story written in their movements. The pattern of their spread reveals the secrets of their parents' death. Astronomers could reconstruct the breakup's violence by studying the spacing of the debris. A tight cluster of fragments would mean a gentle separation. A vast dispersion would suggest an explosive end. The way those trails evolve over weeks or months would help scientists deduce the object's spin rate, internal structure, and how quickly sunlight is pushing on its dust. It's like reading a cosmic autopsy, one light trace at a time. But beyond science, there's something profoundly poetic about the image of an interstellar object scattering itself into starlight. 3IATLAS, a lone traveler from another system, spends millennia untouched, silent, and cold. And then, at the end of its impossible journey, it becomes luminous. It quite literally dies in beauty. Each fragment that drifts away carries a piece of its alien chemistry, atoms forged in another star's furnace, now glowing under our sun. In its destruction, it becomes part of our sky, woven briefly into our nights before fading again into deep space. The debris cloud would not remain static for long. Over time, the gravitational fields of the sun and planets would begin to stretch and distort it. Jupiter, the solar system's biggest bully, would tug at the fragments passing near its orbit, warping their paths like a cosmic magnet pulling on filings. Some pieces might collide with one another, shattering further into dust. Others could spiral inward, slowly drawn toward the sun, their ice vaporizing until they vanish entirely. The smallest particles might even be swept out of the solar system altogether by the constant solar wind, blown back into the interstellar medium from which their parent once came. And yet, for all that motion and change, the debris field would persist in some form for centuries. 1,000 years from now, faint remnants of 3IATLAS's trail might still be drifting quietly through the solar system, cold, dim, forgotten. Every now and then, one fragment might wander too close to a planet's gravity well and plunge inward, a last flicker of light announcing its fall. The rest would just keep going, spreading thinner and thinner until they were indistinguishable from the background dust that fills interplanetary space. If we could step back far enough, say, from the viewpoint of another star, and look at the solar system after the breakup, we might see a faint, ghostly arc curving around the sun. It would look almost like a scar, a trace of something that once passed through. For any distant observer, that faint dust halo might be the only sign that a traveler from another system once came here, lived briefly in the warmth, and then dissolved back into light. There's something deeply human about our fascination with this kind of ending. We see tragedy in disintegration, but the universe doesn't. It doesn't mourn or celebrate. It just transforms. The fragments of 3IATLAS wouldn't be lost. They'd be redistributed. Some would melt into the sun's outer layers. Others would wander through space. And a few might even get caught in the gravity of planets, joining our solar system's family permanently. It's cosmic adoption on a grand scale. In its final act, 3IATLAS becomes more than a single object. It becomes a phenomenon. From one body to thousands, from dark stone to radiant trails. It shifts from being something we can point at to something we can only marvel at. Its death creates not emptiness, but motion, color, and light. 1,000 trails marking the end of an ancient voyage. It came to us as a stranger, but it leaves behind a legacy written across the stars. A shimmering testimony that, even in destruction, there can be wonder. From our planet, we'd see a light show. Telescopes would detect streaks of glowing debris, and maybe, just maybe, a few fragments would enter our atmosphere. Picture shooting stars born from another star system, meteors that traveled light years just to burn up in our sky. It's like the cosmos showing off at a fireworks competition. For astronomers, the first signs of 3IATLAS's grand finale would come quietly, faint, streaking signals across their observatory data. A single speck of light might stretch slightly in long exposure images, betraying motion. Then, another. Soon, telescopes around the world would realize they're not tracking one object anymore, but hundreds, maybe thousands, moving together in a graceful cloud. What was once a mysterious visitor has become an entire light show sweeping through our neighborhood of space. From Earth's surface, the transformation would be mesmerizing. As twilight deepens and the stars begin to emerge, a faint new streak might appear in the night sky. To the casual observer, it might look like a pale, silvery wisp, a ghostly trail curving across the heavens. But with every passing night, it grows more defined, stretching further, shifting subtly as the fragments move along their new orbits. Amateur astronomers would be out in droves, their cameras pointed skyward, chasing this rare visitor's farewell performance. Imagine the headlines. Alien dust cloud illuminates the sky. For weeks or even months, 3IATLAS's remnants could dominate stargazing news. Space agencies would issue bulletins, inviting the public to look up. Observatories from Chile to Hawaii would stream live feeds, showing the debris glinting faintly against the darkness, sunlight bouncing off dust grains that once circled another star. And somewhere in the chatter of social media, someone would inevitably say, "See, the universe does have style." But the real show would begin when Earth crosses paths with the finer dust trails. Every time a planet moves through the leftovers of a comet or asteroid, it's like driving through cosmic confetti. Tiny particles, no bigger than grains of sand, slam into our atmosphere at tens of kilometers per second. Friction ignites them instantly, creating those brilliant, fleeting streaks we call shooting stars. If 3IATLAS's debris intersected our orbit, those meteors would be unlike any other. Genuine interstellar fireflies, each one the last breath of a world far away. It's humbling to imagine. A meteor shower where every flash of light represents something older than the Earth itself. Every streak would be a piece of matter that once orbited another sun, perhaps part of a planet that's now long gone. Some of those fragments could contain exotic isotopes or unfamiliar compounds, chemical time capsules from a place we can never visit. And for a few seconds, they'd blaze across our sky, turning alien dust into beauty before vanishing forever. For the scientists watching from observatories, This wouldn't just be a spectacle, it would be a goldmine of data. Specialized cameras would capture the light spectra of each meteor, breaking down the colors to reveal their elemental makeup. Were they rich in carbon, heavy in metals? Did they contain complex organic molecules? Each flash would tell a new part of the story. The results could confirm what kind of environment 3IATLAS was born in. Perhaps a cool, distant disk of a young star, or the warmer region near a gas giant. For once, we wouldn't have to send probes across the galaxy to study alien material. The galaxy would come to us. If even a slightly larger fragment, say pebble-sized, survived entry, it could reach the ground as a meteorite. The idea of holding a rock that once belonged to another star system is enough to make any scientist's heart skip a beat. It would be physical proof that the void between stars isn't empty. It's full of travelers, carrying secrets from worlds we'll never see. Laboratories would study it grain by grain, scanning for unfamiliar isotopes or molecular structures that might hint at processes different from those that shaped our solar system. It would be like reading a recipe for a planet that doesn't exist anymore. Meanwhile, for the rest of us, it would simply be one of the most breathtaking sights ever witnessed. Imagine lying on a field at night, watching streaks of light that have crossed the abyss between stars. Families, couples, and insomniac poets would all be watching the same thing. Fragments of cosmic history burning up above our heads. Humanity, for once, would be united in wonder rather than worry. The universe has a way of doing that, reminding us how small we are, but also how lucky we are to witness its artistry. The media would go wild, of course. News anchors would toss around phrases like galactic fireworks and alien skyfall, while late-night comedians would joke that Earth's getting unsolicited mail again. But beneath the humor, something deeper would settle in. A shared awe that such beauty could come from destruction. The night sky would no longer just be a canvas of distant stars. It would be a living story unfolding right above us, written in light. And then, after a few weeks or months, it would fade. The fragments would thin out, the trails would disperse, and the meteors would become fewer. The show would be over, leaving behind only memories, and for scientists, reams of data to pore over for decades. 3IATLAS's farewell would join the ranks of celestial events that define generations, whispered about by anyone lucky enough to have seen it firsthand. But perhaps the most profound thought of all would come after the last meteor fades. The knowledge that, for a brief time, something from another star system became part of our world. Its dust touched our skies, its atoms mingled with our atmosphere, and its light danced across our retinas. For all the distances that divide the stars, this was proof that the universe occasionally lets us touch hands across the void. So when we look up and see that final spark, a grain of interstellar dust burning its last in our sky, we're not just witnessing destruction, we're seeing connection. The cosmos doesn't just show off, it shares. And in those fleeting streaks of light, Earth becomes, however briefly, part of a story that began light years away. But not all sparkles are safe. If even one large fragment intersected Earth's orbit, it could pose a real threat. A piece the size of a small building could release energy comparable to a nuclear explosion if it hit. Imagine explaining that on the news. Interstellar rock ruins everyone's weekend barbecue. For all its beauty, space doesn't always play nice. Every meteor that burns harmlessly in our atmosphere has a much meaner cousin, the kind that doesn't stop burning until it hits something important. And when you're dealing with fragments of an interstellar object, the stakes get much higher. These pieces aren't native to our solar system. They're moving faster, they're harder to track, and they're made of who knows what. If 3IATLAS's breakup sprayed a few big shards onto intersecting paths with Earth, we'd be dealing with something no planet ever wants: a cosmic hit and run. Let's start with the basics of impact physics, the universe's least forgiving math. A rock the size of a car hitting Earth at typical asteroid speeds, around 20 kilometers per second, releases energy roughly equivalent to a few tons of TNT. But interstellar fragments, like those from 3IATLAS, could be moving more than twice that speed, 40, 50, even 60 kilometers per second. That's not just fast, that's blink and it vaporizes fast. Kinetic energy scales with the square of velocity, so double the speed means 4 times the punch. In other words, a building-sized chunk of alien debris wouldn't just make a crater. It would make headlines, seismic waves, and possibly a new entry in the things that ruined human civilization record book. Now, the odds of such an impact are small. Space is enormous, and even after the debris spreads, most of it would miss us entirely. But small odds doesn't mean impossible. Earth has been hit before by asteroids, comets, and all manner of stray objects. What makes interstellar fragments unique is that they arrive with almost no warning. Traditional asteroid detection relies on tracking objects that orbit the Sun, predictable, repeatable paths. Interstellar debris doesn't play by those rules. It could approach from any direction, at any speed, with almost no time for us to prepare. Imagine a future scenario. Telescopes spot a faint object streaking across the sky, and after a quick analysis, astronomers realize it's a fragment of 3IATLAS, one that's heading straight toward us. Panic? Maybe not immediately, but there would be some serious coffee being consumed at NASA. Tracking interstellar debris is tricky. Their high velocities mean even a tiny miscalculation can shift predictions by thousands of kilometers. Scientists would run simulations, calculating possible impact zones, all while the world refreshes social media like it's a global weather forecast. Let's say one of those fragments, maybe the size of a house, does hit. What would that look like? Well, first off, you wouldn't see a slow, cinematic descent. It would enter the atmosphere at such high speed that it would compress the air in front of it into a fireball hotter than the surface of the sun. The shockwave alone could flatten buildings for miles. Even if it exploded before reaching the ground, the resulting airburst could rival the force of a nuclear detonation, minus the radiation, plus the bragging rights of being destroyed by an alien rock. Events like that have happened before, albeit with local ingredients. The Tunguska explosion in 1908, which leveled a Siberian forest the size of a major city, was caused by a space rock roughly 50 meters wide. Now imagine something similar, but traveling twice as fast, with a composition no one's ever seen before. If it landed in the ocean, it could trigger tsunamis. If it hit near a city, the damage would be catastrophic. Earth's atmosphere might shield us from most small debris, but for anything larger than a few dozen meters, we're in the hope it lands somewhere empty zone. Governments and space agencies have impact monitoring systems, of course. NASA's Planetary Defense Coordination Office keeps an eye on near-Earth objects, and observatories worldwide contribute to the watch list. But, again, interstellar fragments, like 3IATLAS's offspring, don't follow local rules. They're like uninvited guests who don't show up on the guest list until they're already at the door. Detecting them requires scanning vast portions of the sky constantly, a cosmic version of Where's Waldo, played at relativistic speeds. Beyond the physical threat, there's also the psychological one. Humanity doesn't react calmly when things fall from the sky. A visible, high-velocity object burning through the atmosphere could trigger widespread panic, even if it misses entirely. People might think it's a missile, or worse, something sent intentionally. Governments would scramble to explain, astronomers would rush to reassure, and conspiracy theorists would immediately upload 12-hour YouTube documentaries titled Alien Strike: The Truth NASA Hides. But amid the fear and fascination lies a silver lining. Every potential hazard is also an opportunity for understanding. If a fragment did survive impact, the resulting crater and the material it left behind would be priceless to science. It would be the first time in history we could physically study interstellar rock on Earth's surface. Teams would rush to collect samples before contamination, analyzing their isotopic ratios, minerals, and trace gases. What we could learn might redefine our understanding of how solar systems form and evolve. The cost of that knowledge, however, would depend heavily on where the rock landed, preferably not on a major city. In a broader sense, 3IATLAS's fragments remind us of something we often forget. Our planet isn't a stationary, safe haven. It's a moving target in a shooting gallery of celestial debris. Most of the time, the universe misses. Occasionally, it doesn't. And while the sight of glowing alien dust painting the sky is awe-inspiring, it's also a quiet warning that beauty and danger often share the same orbit. So, as we marvel at the cosmic fireworks, let's not forget the other side of the story. Every twinkling spark could be a gentle goodbye or a fast-approaching hello. The universe is generous with wonder, but it also keeps us humble. After all, it takes only one misplaced fragment to turn interstellar spectacle into breaking news. And somewhere, perhaps, 3IATLAS would be proud. Not because it caused chaos, but because it reminded us just how thin the line is between awe and alarm in the great cosmic dance. A shattered 3IATLAS wouldn't just affect us. Space agencies and satellites would have to track thousands of new high-speed projectiles, zooming through the inner solar system. The debris could cross paths with spacecraft or even the orbits of planets. Space just got a lot more crowded, and cleaning it up, well, that's not in anyone's budget. You've probably heard of traffic jams on Earth, cars honking, tempers flaring, people late for meetings. Now imagine that same concept, but in space. And instead of cars, it's hypervelocity shards of alien rock zipping around at tens of kilometers per second. No horns, no stoplights, just chaos in slow motion. That's what a shattered 3IATLAS would unleash on the solar system. A celestial traffic snarl that makes rush hour in Los Angeles look like a yoga retreat. Once 3IATLAS fractures into thousands of pieces, those fragments begin to spread into distinct streams. Some are small enough to be harmless dust, but others, perhaps boulder-sized, pose a real challenge. Each one follows a new path determined by the explosion's force, the sun's gravity, and the gravitational nudge of nearby planets. The result isn't a neat, well-behaved comet trail, but a sprawling, tangled mess of interstellar debris weaving through the solar system's busiest lanes. Let's start with the immediate problem, tracking it all. Space agencies already keep tabs on over 30,000 objects orbiting Earth. Defunct satellites, rocket parts, lost wrenches, and everything in between. And that's just local junk. Add to that a sudden influx of alien debris screaming through the inner solar system, and the situation becomes a cosmic logistics nightmare. Ground-based observatories would scramble to detect and map the fragments. But even the best radar and optical systems have limits. These pieces would be small, dark, and fast, like trying to spot a swarm of black marbles flying through a blizzard. The problem is compounded by perspective. Objects in space don't just sit still, waiting to be found. They move constantly. A fragment might appear harmless 1 week, then suddenly shift course as it passes. Near Venus or Mercury, their gravity bending its trajectory just enough to make it unpredictable. Even a fragment only a few meters across could ruin a spacecraft's day if it happened to be in the wrong place at the wrong time. And since many interstellar fragments wouldn't follow the same plane as our planet's orbits, they could come from any direction. The ultimate blind spot problem. Now, imagine being at NASA's Jet Propulsion Laboratory or the European Space Agency's Mission Control as this unfolds. Monitors would be filled with trajectories, warnings, and red dots representing possible collision paths. Mission planners would need to run continuous recalculations to ensure spacecraft like the James Webb Space Telescope, Mars orbiters, or upcoming asteroid missions aren't in harm's way. Spacecraft might even have to adjust their orbits, burning precious fuel to steer clear of potential impacts. It's the ultimate cosmic version of duck and cover. And this doesn't just concern robots. Future crewed missions to the Moon or Mars would also face new hazards. A fragment of 3IATLAS, the size of a baseball, could punch straight through a habitat module or puncture a spacesuit before anyone even knew it was coming. In space, size doesn't always equal danger. It's speed that kills. A grain of sand moving at tens of kilometers per second carries the impact energy of a bullet. Thousands of such particles sweeping through the solar system would turn certain orbits into no-go zones until the debris disperses. Meanwhile, back on Earth, the data deluge would be immense. Astronomers and engineers would feed everything into complex models predicting the long-term evolution of the debris cloud. Would it stay in the inner solar system? Would it scatter outward toward Jupiter's domain? Or would some of it settle into stable orbits, effectively becoming a new population of artificial comets circling our sun? The answers wouldn't come quickly. Gravitational interactions are chaotic, and even small changes in initial velocity can completely alter a fragment's fate. There's also the question of ownership and responsibility. Who owns alien debris? If a chunk of 3IATLAS damages a satellite worth billions, who foots the bill? International space law doesn't have a clause for collisions caused by shattered interstellar objects. Insurance companies would probably call it an act of the cosmos, not their problem. The event would ignite a frenzy of policy debates. Should we develop protocols for managing interstellar debris? Could we even do anything about it if we tried? After all, we're still struggling to clean up the junk we've already left in orbit. And speaking of cleanup, forget it. You can't just sweep space. Even collecting local space junk is nearly impossible. Now imagine trying to deal with thousands of pieces, traveling across millions of kilometers at astronomical speeds. There's no net big enough, no spacecraft agile enough. The best we could do is wait and watch, hoping the sun's radiation pressure and planetary gravity eventually scatter the fragments into safer, more distant orbits. In other words, we'd be relying on celestial janitorial services, a process that might take centuries. Yet, amid the logistical headaches and orbital hazards, there's an odd fascination to it all. A shattered interstellar visitor, turning our solar system into a temporary traffic jam, would be an unprecedented natural experiment. Scientists could study how dust and debris interact with solar radiation, how gravity shapes their evolution, and how collisions between fragments generate new, smaller particles. It would be like watching planetary formation in reverse, a system breaking apart instead of coming together. Still, the poetic chaos of it all doesn't erase the risk. Every satellite operator, every mission planner, every space agency would have to adapt to this new reality. The solar system would briefly become more alive, dynamic, unpredictable, and slightly dangerous. For a species that's just learning to stretch its legs beyond Earth, that's a sobering reminder that space isn't empty. It's an ever-changing ocean of motion, where even a single shattered traveler from another star can stir the tides. So yes, The night sky might look stunning, streaked with glimmers of alien dust. But beneath that beauty lies a challenge we've never faced before: interstellar congestion. The cosmos doesn't issue traffic reports, and when it decides to send a few thousand high-speed visitors through our neighborhood, we're left scrambling to dodge them. The stars may seem distant and serene, but moments like this remind us, even out here, the universe has its own brand of gridlock. On the bright side, scientists would have a field day. Each fragment is a sample from another star system, the ultimate interstellar gift basket. Spectrographs could study their composition, revealing clues about distant planetary systems. It would be like finding a meteorite that says, "Greetings from Alpha Centauri." If 3IATLAS broke apart, it wouldn't just be an astronomical event. It would be a scientific windfall, unlike anything humanity has ever encountered. For the first time in history, we'd have direct access to physical material from another star system, not through a probe, not through radio signals, but literally falling into our observational reach. In one instant, our corner of space would transform into a galactic laboratory, and scientists around the world would be scrambling like kids on a cosmic Easter egg hunt. The excitement would begin the moment the breakup was confirmed. Observatories across the globe, from Hawaii's Mauna Kea to Chile's Atacama Desert, would turn their eyes toward the expanding debris field. Every telescope capable of catching light would be repurposed to track the fragments, analyze their reflections, and collect their spectral fingerprints. Each line and dip in a spectrum tells a story: what elements the fragments contain, what ices evaporate under sunlight, even how the surface texture scatters light. It's like reading the autobiography of an alien rock, written in wavelengths instead of words. To the naked eye, all those fragments might look like faint, shimmering dots. But to a spectrograph, they're treasure chests of information. Scientists could detect unfamiliar isotopic ratios, maybe oxygen that's slightly heavier than ours, or carbon patterns that don't quite match anything in our solar system. These subtle differences would reveal how the chemistry of other star systems diverges from our own. It's a rare glimpse into the diversity of planetary formation across the galaxy. For context, we've only ever studied materials from our solar system, lunar samples, meteorites from Mars, and dust from comets. Interstellar debris would rewrite the entire baseline of what normal even means. And here's the thrilling part: not all those fragments would stay out of reach. Some might eventually intersect Earth's orbit, giving us a chance to physically collect interstellar material. Agencies like NASA, ESA, and JAXA would race to design interception missions. Small spacecraft equipped with collectors to scoop up dust particles or analyze them on the fly. It would be like catching snowflakes from another world. The data would be priceless, the kind that earns Nobel Prizes and rewrites textbooks. For planetary scientists, this would be the closest thing to a galactic census. Each fragment could tell them how common certain compounds are across different stellar nurseries: ammonia, methane, silicates, carbonates. Do other star systems favor the same chemical recipes that seeded life here? Or are we outliers, an odd little chemistry experiment that happened to work? A few molecules of alien dust could begin to answer those questions. Geologists, too, would be ecstatic. The structure and density of the fragments would hint at the conditions under which they formed. Was 3IATLAS built in the cold outer reaches of its home system, where ices dominate, or in the warmer inner regions where rock prevails? Tiny differences in mineral crystals, their shape, their layering, would reveal the story of pressure, heat, and time. Each fragment becomes a fossilized memory of a world that once might have been. Even astrobiologists would join the chase. The question of life's ingredients has always haunted humanity. Are the building blocks of biology, amino acids, sugars, simple organics, common across the cosmos? If 3IATLAS carried even trace amounts of these compounds, it would mean that the chemistry of life isn't confined to our solar system. It would suggest that the seeds of biology might drift freely between stars, hitching rides on icy wanderers like 3IATLAS, waiting for a planet warm and wet enough to start something new. The idea that our origins could be shared across the galaxy would move from speculation to evidence. And it's not just about what's inside the fragments. It's about how they behave. As they interact with sunlight, as their gases sublimate, as they fragment further, scientists would get a first-hand look at the physics of interstellar materials. How do ices formed around other stars respond to our sun's heat? How reflective are they? How cohesive is their structure? Every question answered would open 10 new ones, each peeling back another layer of mystery about the diversity of worlds beyond our own. Of course, managing this avalanche of discovery would be a logistical feat. International collaborations would spring up overnight. Data from radio telescopes, optical observatories, and space probes would pour into shared databases. It would be the most globally unified scientific effort since the detection of gravitational waves. Perhaps even more so. Scientists would hold emergency conferences, drafting plans to coordinate resources, while students and citizen astronomers everywhere would participate, submitting their own observations. For a brief, shining moment, Earth's scientific community would pulse as one organism, staring outward together into the deep unknown. And let's not overlook the human side of this jackpot. Beyond the measurements and analysis lies a powerful emotional truth. We'd be studying something that physically came from another star. Not light, not radiation, but matter. Real, tangible atoms that formed under a sun we'll never see. There's poetry in that. For all our technological progress, this would be the ultimate act of curiosity. The universe delivering a message in a bottle, and us, finally, with the tools and the humility to read it. Even decades later, scientists would still be mining the data. Museums would display tiny flecks of interstellar material encased in glass, visitors staring in awe at something that once drifted between suns. It would remind us that we're not isolated, not alone. The galaxy is a vast exchange of material, dust, rock, and maybe even life itself, constantly swapping between star systems like cosmic postcards. So yes, 3IATLAS, breaking apart might be messy, unpredictable, and even dangerous. But for science, it would be the event of a lifetime. It's as if the universe, after eons of keeping its secrets to itself, finally decided to hand us a sample and say, "Here, study this, see if you can figure me out." And you can bet humanity would rise to the challenge, magnifying glasses ready, curiosity blazing, eager to learn what stories those fragments whisper from across the stars. By analyzing the dust and ice, we could learn whether 3IATLAS carries exotic elements or unusual organic molecules. Maybe its chemistry hints at how planets form elsewhere, or even whether the building blocks of life are more common than we thought. In a way, its breakup could spill cosmic secrets, a universe overshare, if you will. The moment 3IATLAS fractured into 1,000 glittering fragments, it didn't just create a celestial spectacle, it opened up a chemical treasure chest. Every wisp of vapor and grain of dust spilling into space would be a data point, a chemical clue, a whisper from another world. For scientists who study cosmic chemistry, this would be like Christmas, New Year's, and the discovery of fire all happening on the same day. Let's start with what happens when the fragments begin to sublimate, when the sun's warmth coaxes frozen materials into vapor. Those gases don't just vanish, they glow, forming spectral lines that telescopes can detect. Each element and molecule leaves a distinct signature, like a barcode in light. By reading those patterns, astronomers could deduce the exact chemical recipe inside 3IATLAS. The results could confirm what we already know about comets, or more tantalizingly, upend everything. Consider this. Every solar system in the galaxy forms under slightly different conditions. The ratio of carbon to oxygen, the abundance of heavy elements, the radiation from nearby stars. All of these factors tweak the chemical mix that planets, moons, and comets inherit. If 3IATLAS came from a region rich in carbon, for instance, its dust might contain exotic hydrocarbons or long-chain organic molecules rarely seen in our local comets. If it formed closer to a massive star, it might carry rare isotopes forged in intense stellar winds. The sun's light, breaking through the gas cloud around each fragment, would reveal all of that in spectral fingerprints. A literal rainbow of alien chemistry. Scientists would study not only what elements are present, but how they're bonded together. Are there amino acids, the precursors to proteins? Simple sugars like ribose? Nitriles, which can help form nucleic acids? These are the Lego bricks of biology, and if 3IATLAS contains even a trace of them, it would suggest that nature builds these molecules everywhere, not just in our solar system. That wouldn't necessarily mean life is common, but it would mean the universe is at least trying to make it. Chemistry, it seems, is eager to experiment. And here's where things get really fascinating. The isotopes. Isotopes are like atomic accents, subtle variations in the same element that reveal where and how it was made. The ratio of heavy hydrogen, deuterium, to normal hydrogen, for example, can tell scientists how cold an object's birthplace was. If 3IATLAS's ice has a different deuterium ratio than Earth's oceans or local comets, it could mean it formed in a region of its home system far colder or warmer than any place we've studied. That single measurement could redraw our map of what environments exist in other planetary nurseries. Now, imagine a fragment of 3IATLAS venting a plume of vapor, gases escaping like sighs from the deep freeze of another star system. Instruments aboard orbiting observatories, or maybe even a purpose-built probe, would catch that vapor and dissect its spectrum in real time. If we detect something never before seen, a complex organic molecule that doesn't form naturally under known conditions, it could challenge our understanding of chemistry itself. Perhaps other stars create environments where exotic molecules, unstable here, thrive there. It would be like finding out that nature has been running a parallel laboratory across the galaxy, and we've just glimpsed one of its experiments. There's also the question of chirality, a word that sounds fancy but really just means handedness. Many organic molecules come in two mirror image forms, like left and right hands. On Earth, life overwhelmingly uses one version over the other. But if 3IATLAS's organics show the opposite orientation, it would mean that even if life exists elsewhere, it could be biochemically incompatible with ours. That realization would be both thrilling and humbling. Life could be universal, yet fundamentally alien in its very structure. Of course, studying these materials wouldn't be easy. Many of the compounds would break down quickly under sunlight, so timing would be everything. Observatories would race against evaporation, collecting data before the fragments faded into dust. A coordinated global effort would emerge, telescopes tracking the infrared glow of ices, space-based sensors capturing ultraviolet emissions, even amateur astronomers photographing faint color changes in the debris cloud. The whole planet would become one giant laboratory pointed toward the same mystery, and the discoveries wouldn't stop at organics. The mineral makeup of 3IATLAS's dust could hold just as many surprises. Imagine finding crystalline silicates that formed under pressures far higher than anything seen in our solar comets, or traces of metals enriched by nearby supernovae. Maybe even minerals that require compounds absent in our solar system. Alien geology at the molecular level. Each new compound identified would be a fingerprint from a star we've never seen. a tiny piece of its personality carried across light years. To the scientific community, this would mark a turning point. The first tangible comparison between our solar chemistry and someone else's. For centuries, humans have wondered whether the laws of physics and chemistry are truly universal. If the molecules inside 3IATLAS mirror our own, it would confirm that nature follows the same rules everywhere. But if they differ, even slightly, it would mean there are other ways for matter to organize itself, other recipes for building worlds, and maybe even other paths to creating life. And the public reaction? Awe, of course. Once the headlines start rolling, alien molecules found in solar system visitor, everyone from school children to philosophers would be asking what it means. The idea that we can identify chemistry from another star system, that we can literally see the fingerprints of an alien sun, would forever change how we think about our place in the cosmos. 3IATLAS's breakup might look like chaos, fragments, vapor, and dust scattering in all directions. But to scientists, that chaos is information. Every molecule released, every photon absorbed and re-emitted is a clue to the grand chemical story of the universe. It's as if the cosmos finally opened its notebook, and for a brief, shining moment, we get to peek at the pages. So yes, it would be a universe overshare, and a glorious one at that. Because for all our theories and equations, nothing compares to holding proof in our hands, or rather, watching it drift past our telescopes in clouds of glowing gas, whispering secrets from the chemistry of another world. Over time, solar radiation and gravitational nudges would scatter the fragments across the solar system. Some would fall into the sun, others would escape into deep space again. A few might linger for centuries, slowly fading, like the remnants of a long-forgotten campfire. The interstellar visitor would vanish, but its ghostly fingerprints would remain. Every ending in space happens quietly. There's no applause, no curtain call, just the slow unwinding of motion until even the memory fades into background starlight. After its brilliant moment of chaos, 3IATLAS would begin its long farewell tour, a slow, graceful disintegration that could last longer than human civilization itself. What began as a violent breakup would end in a kind of celestial whisper, the universe returning to its normal rhythm as if nothing had happened. The first to disappear would be the smallest pieces, the fine dust grains, barely larger than smoke particles. The solar wind, that constant outflow of charged particles from the sun, would buffet them relentlessly. Each grain would be pushed outward by the pressure of sunlight, sailing away like microscopic ships on a wind made of photons. To an observer with a powerful telescope, the debris cloud would gradually stretch and fade, its edges thinning as the smallest fragments were carried out of the inner solar system. Larger pieces would resist the push for longer. Some might settle into temporary orbits, looping lazily around the sun in elongated ellipses. These survivors would become honorary members of our solar family, cosmic squatters from another star, quietly circling among the native asteroids and comets. A few might even pass near the outer planets, where Jupiter's immense gravity could bend their paths into new trajectories. Some would be captured, others flung outward like cosmic boomerangs, launched once again into the great interstellar sea. The galaxy, it seems, has a way of returning its travelers home. But for the fragments drawn too close to the sun, there would be no second journey. The sun is a patient predator. Over months or years, these pieces would spiral inward, their orbits decaying with every pass. As they neared the solar furnace, their ices would boil away completely, leaving behind nothing but mineral dust. Eventually, they'd fall into the sun itself, not in a fiery blaze, but quietly, swallowed whole by the very star whose warmth ended their ancient journey. Their atoms would mix with the sun's plasma, fusing into its endless churn of light. The irony is almost poetic. After wandering for eons through darkness, the final destination of 3IATLAS's fragments would be to become part of the light that illuminates other worlds. Those that escaped the solar system, though, would embark on an even lonelier voyage. Flung by Jupiter or nudged by solar radiation, they'd drift beyond the reach of the planets, heading back into the interstellar void. There, in the cold silence between stars, they join the galactic dust, tiny ambassadors of a story that began long before Earth existed. They might pass near other star systems millions of years from now, just as their parent once passed ours. Maybe they'd be noticed again by some distant civilization, peering through their own telescopes and wondering where this stray visitor came from. In that way, 3IATLAS wouldn't really vanish. It would just move on to another chapter, one we'll never get to read. For centuries, though, echoes of its presence might still linger around our sun. Some fragments would remain in stable or semi-stable orbits, their paths stretched into long, lazy ellipses. They'd cross the inner solar system now and then, faint and forgotten, leaving traces of dust that might occasionally create small meteor showers. Perhaps hundreds of years from now, an observer on Earth would notice a brief flurry of shooting stars, the final remnants of a long-gone interstellar visitor, announcing itself one last time before fading completely. In a sense, the universe specializes in goodbyes like this. It never erases, it erodes. The marks of passing things are subtle, a faint spectral trail, a chemical signature, a tiny shift in orbital debris. Even as 3IATLAS disappears, it leaves behind data, etched into the instruments of every telescope that watched it, into the archives of observatories, into the stories of those who saw it blaze across the sky. Its physical body might dissolve, but its legacy endures in the collective curiosity it sparked. And there's a melancholy beauty in that endurance. For billions of years, 3IATLAS drifted alone, unseen, carrying with it the history of another star. For a brief moment, it crossed paths with us, a planet of thinking creatures who noticed it, named it, and wondered about its origins. Then, as quietly as it came, it moved on. In the grand scale of cosmic time, its visit was nothing more than a flicker. But, in that flicker, it bridged two worlds that will never meet again. Astronomers might continue tracking the largest fragments for decades, watching their slow dispersal. Each new observation would reveal another stage of decay, brightness fading, orbit widening, the traces of outgassing dwindling to nothing. The data would form a timeline, a record of how interstellar debris behaves under our sun's influence. Even in disappearance, 3IATLAS would still be teaching us. Eventually, though, the last trace would vanish. No dust, no glow, no radar blip. The interstellar traveler would dissolve completely into the tapestry of cosmic background noise. Future generations might find references to it in scientific papers and wonder what it looked like, what it taught us, and what it felt like to witness an object from another star system disintegrate before our eyes. By then, the universe would have sent new visitors, new mysteries, and the memory of 3IATLAS would settle into history. A ghostly echo of discovery. But maybe that's the quiet triumph of its story. It didn't just pass through, it left fingerprints. On our senses, on our science, and on our sense of wonder. The long goodbye of 3IATLAS isn't really an ending at all. It's a reminder that even fleeting things can leave permanent marks, that even the briefest visitor can change the way we see our place in the cosmos. In time, its fragments will fade into the dark, but its lesson will stay, that the universe is always moving, always exchanging, always saying goodbye in one place and hello in another. The light we see tonight may carry atoms that once belonged to it, drifting still, unseen, across the endless gulf, whispering softly that nothing in the universe is ever truly lost. Every cosmic event leaves ripples in our understanding. The breakup of 3IATLAS would challenge how we model interstellar bodies, their strength, composition, and survival near stars. It might even rewrite parts of our textbook on cometary physics. Science loves a good mystery, especially when it explodes into smaller, measurable pieces. If there's one thing astronomers adore, it's when the universe throws them a puzzle wrapped in chaos. The breakup of 3IATLAS would be more than just an astronomical curiosity. It would be a paradigm shaker. Every telescope aimed at the event, every line of data recorded, would send shockwaves through multiple fields of study. What we thought we knew about comets, asteroids, and interstellar visitors would be put to the test, and chances are we'd find out that nature once again outsmarted us. For starters, the event would challenge our understanding of material strength in space. Until now, models of cometary and interstellar bodies have relied heavily on assumptions, a blend of educated guesswork and the occasional, lucky observation. When Oumuamua and 2I Borisov zipped through the solar system, we learned that interstellar objects could behave very differently from local ones, but their flybys were fleeting, giving us only fragments of insight. 3IATLAS, breaking apart, however, would offer a rare, slow-motion case study. Scientists could analyze the timing, pattern, and velocity of the fragments to estimate the object's internal cohesion, how strongly it held together. Did it crumble because it was weak and porous, or because internal gases built up too much pressure? If the fragments broke into neat clusters, it might suggest a layered structure, perhaps a crust of hardened material, encasing softer, icy cores. If it burst into irregular shards, it might mean its composition was patchy or uneven. These clues could completely change our theories about how such interstellar objects survive the harsh environments between stars. Then there's the question of thermal tolerance. How much heat can an interstellar object endure before disintegrating? Most models are based on comets that formed under our sun's influence. But 3IATLAS came from an entirely different nursery. If it broke apart closer to the sun than expected, it might mean alien ices are more volatile. They vaporize at lower temperatures. If it survived longer than anticipated, it could indicate exotic materials or stronger chemical bonds. Either result would refine the way we estimate how these cosmic travelers evolve as they encounter stars. And of course, the data fallout from this event would be immense. Observatories across the spectrum, from optical telescopes to radio dishes to infrared sensors, would collect terabytes of information. Artificial intelligence models would be trained to track fragment motion, analyze dust spectra, and simulate possible internal structures. This wouldn't be just one discovery, it would be thousands cascading through research papers for decades. The ripple wouldn't stop with cometary physics. It would extend into planetary science, astrochemistry, and even the study of how solar systems form. One particularly intriguing ripple would touch on planet formation theory. The chemical and physical characteristics of 3IATLAS's fragments could provide a rare look at the early stages of a different star system. By comparing the ratios of rock to ice or the density of the fragments, scientists could infer how efficiently that distant system formed solid bodies. Were its comets more icy or rocky? Did its star produce a similar mix of elements to our sun, or something wildly different? Every answer would refine our models of how common or rare systems like ours might be. There's also a philosophical ripple, the one that runs through the scientific community itself. Events like this have a way of reinvigorating fields that had grown comfortable. Suddenly, old theories are up for re-evaluation. Researchers who've spent years studying quiet, predictable comets would find themselves debating new hypotheses late into the night. Do interstellar bodies form in the same way as local ones? Are their structures shaped by different pressures, or even by different chemical building blocks altogether? Conferences would buzz with energy, academic journals would fill with fresh studies, and graduate students would be gleefully drowning in thesis topics. Another ripple would reach into technology and observation methods. A sudden high-profile breakup like 3IATLAS's would push the limits of our instruments. Tracking thousands of faint, fast-moving fragments would require precision and innovation. Astronomers might develop new algorithms to handle dynamic systems in real time, leading to improvements in space debris tracking, asteroid defense, and deep space imaging. In a very real sense, chaos in the sky forces us to get smarter on the ground. Even beyond the science labs, the event would ripple through the public imagination. The idea that our skies were briefly filled with glowing debris from another star would become a cultural touchstone, a symbol of connection between distant worlds. Artists, writers, and filmmakers would seize on the imagery of alien dust scattering through the solar system. The story would transcend science, inspiring a new generation to look up and wonder what else is wandering out there waiting to surprise us. Meanwhile, within the scientific community, one deeper ripple would persist: humility. Every major discovery has a way of reminding us how little we actually know. The breakup of 3IATLAS would show that even with all our instruments, we're still just beginning to grasp how diverse and unpredictable the universe really is. Maybe most interstellar visitors are fragile. Maybe they're tougher than we think. Or maybe 3IATLAS is just one example among countless variations we haven't met yet. And yet, that's what makes science beautiful. Each cosmic mystery we unravel only reveals a dozen more waiting behind it. The ripple effect isn't just about data. It's about curiosity expanding outward, reshaping our questions, forcing us to see familiar things with new eyes. So yes, the explosion of 3IATLAS would scatter fragments across the solar system. But the true debris would be intellectual, a shower of new ideas, new models, and new questions raining down across every branch of astronomy. Long after its physical remnants faded into the dark, its influence would persist in our equations, our research, and our imaginations. Every cosmic visitor changes us a little. But 3IATLAS's breakup would do more than that. It would remind us that knowledge, like gravity, spreads. One shattered object could ripple through decades of discovery, reshaping how we see the stars, and perhaps how we see ourselves among them. The headlines would be wild. Alien rock explodes. Cosmic shrapnel lights up the sky. Half the world would panic. The other half would live stream it. Scientists would calmly explain it's mostly harmless, while conspiracy theorists would insist it's space breadcrumbs from an alien invasion. Either way, humanity would watch the sky with collective awe and a little unease. When something from another star breaks apart in our backyard, you can bet the news cycle would lose its collective mind. At first, the story would trickle through science channels and astronomy blogs, all measured tones and technical terms. Interstellar object undergoes fragmentation event, the headlines would read. Then someone would upload a grainy cell phone video of the night sky, streaked with glowing fragments. And suddenly, It's not a niche astronomy story anymore. It's a global spectacle. The media would latch on like cosmic glue. Every network would have its own spin. The sober outlets would call it a historic astronomical event. The more excitable ones would go straight to alien visitor explodes near Earth. Social media would drown in hashtags. Hashed Atlas, shattered. Hashed cosmic fireworks. Hashed interstellar apocalypse. News anchors would gesture at glowing trails on screen, while animated graphics of asteroids zoomed dramatically past digital Earths. And through it all, astronomers would be desperately trying to get a word in. No, it's not dangerous. No, it's not aliens. Yes, it's very pretty. But humanity being humanity, not everyone would listen to the calm explanations. The internet would do what the internet does best: speculate wildly. One group would argue that 3IATLAS was clearly an alien probe self-destructing after finishing its mission. Another would swear it's a government cover-up, that world powers secretly knew it was coming. A third faction would link it to ancient prophecies, because somewhere in a 400-year-old book, someone once mentioned a star that breaks into 1,000 lights. Within days, there would be documentaries, podcasts, and 12-hour YouTube analysis videos featuring ominous music and pixelated zoom-ins of glowing fragments. Meanwhile, scientists would be on every talk show they could find, smiling politely as they tried to steer the conversation back to reality. It's just a natural event, they'd explain. It's a rare chance to study an interstellar object up close. Some viewers would nod, comforted by rational voices. Others would decide these experts were clearly lying because they seemed too calm. The pattern would be familiar, a mix of awe, confusion, and that irresistible human instinct to make meaning out of mystery. Then there would be the observers, millions of ordinary people stepping outside, looking up, and realizing they're watching something truly cosmic unfold in real time. From cities to deserts, people would gather in backyards and parks, staring at faint streaks crossing the sky. Kids would point and cheer. Parents would fumble to explain what they're seeing. Couples would whisper about how tiny they suddenly feel. Even amid the noise of panic and memes, something deeper would resonate. That sense of wonder we always feel when the universe decides to remind us how big it is. Religions would weigh in too, of course. Some would call it a sign, others a test, others simply proof of creation's vastness. Poets would write about a sky unzipped by light, while artists would paint the shattered trails as celestial veins. Musicians would release songs inspired by the visitor that came undone. The event would seep into culture in ways that science alone couldn't contain. It wouldn't just be data, it would be mythology in the making. Governments would have their own reactions, balancing between calm reassurance and logistical preparedness. Space agencies would hold press conferences outlining how they're tracking the fragments, making sure none pose a danger to satellites or planetary systems. military agencies would quietly double-check radar systems, just to be sure. Somewhere, a few defense analysts would write a report titled something like Potential Implications of Interstellar Object Fragmentation for Planetary Security. You know, just in case. And then there'd be the inevitable flood of opportunists. Companies would advertise interstellar fragment jewelry made of fake meteorite dust. Influencers would sell 3IATLAS cleansing crystals on live streams. Tourism boards in dark sky regions would offer view the alien fireworks getaway packages. Somewhere, a film studio would fast-track a movie, Atlas Rising, based on true events. Humanity would do what it always does, find a way to make money from cosmic wonder. But beneath the frenzy, something more enduring would take root: curiosity. Millions of people, many of whom had never cared about astronomy before, would suddenly be reading about spectroscopy, orbital mechanics, and interstellar chemistry. Schools would organize stargazing nights. Online searches for what is an interstellar object would skyrocket. For a generation growing up with more screens than skies, 3IATLAS's breakup would be a wake-up call, a reminder that the universe isn't just a backdrop. It's alive, dynamic, and sometimes breathtakingly dramatic. As the weeks passed and the light show faded, the panic would subside. The memes would slow down, the headlines would shrink, and scientists would go back to their data. But something would linger, a quiet fascination, a collective memory of when everyone on Earth looked up at the same time. The event would become one of those "where were you when" moments, the kind people talk about years later. "I remember that night," someone would say. "I saw the interstellar comet break apart. It was like the sky cracked open." And maybe, just maybe, humanity would come out of it a little more united in perspective. For once, it wouldn't be about borders or politics. It would be about something bigger than all of us. A shared experience of insignificance and wonder. Because when a rock from another star system disintegrates above your planet, lighting up the night sky, it doesn't matter who you are or where you're standing. You're part of the same story, looking at the same sky. In the end, 3IATLAS wouldn't just scatter dust and data. It would scatter inspiration. It would remind us how small we are, yes, but also how connected to each other, to the stars, to everything that drifts between them. Humanity's reaction, in all its chaos, comedy, and curiosity, would reflect exactly what makes us human: our endless need to understand, to feel, and to turn every burst of cosmic light into meaning. Eventually, the excitement would fade, the fragments would disperse, and 3IATLAS would become another chapter in the cosmic diary. But its breakup would remind us how dynamic, unpredictable, and downright dramatic the universe can be. Space doesn't just sit quietly. It throws tantrums made of stardust. And sometimes, those tantrums are how we learn what the universe is really made of. For a brief window in time, 3IATLAS dominated our skies, our headlines, and our imagination. But, as with all great celestial events, the curtain would slowly close. The glowing trails would dim. The debris cloud would stretch thinner, fainter, until it blended into the background of interplanetary dust. Astronomers would move their telescopes onto new targets. Data sets would be archived, and people would go back to worrying about weather forecasts instead of orbital trajectories. The cosmos, having delivered its performance, would slip back into quiet indifference. That's the thing about the universe. It never lingers. Even the most awe-inspiring events are fleeting against its timescale. Stars explode, galaxies collide, planets form and vanish, and through it all, the cosmos just keeps moving. What feels monumental to us is, to the universe, just another day at the office. The shattered remains of 3IATLAS would scatter invisibly through the solar system, their motions dictated not by memory or meaning, but by math, a graceful, eternal dance choreographed by gravity. But just because the universe moves on doesn't mean we do. Humanity has a habit of holding on to the echoes. The breakup of 3IATLAS would become one of those events that live on in the collective imagination, a symbol of both cosmic impermanence and discovery. Textbooks would record its data, documentaries would recount its story, artists would capture its beauty long after its last fragment faded. We turn it into a lesson about curiosity, about transience, about the rare privilege of being able to witness a visitor from beyond the stars. Somewhere in the archives of observatories, terabytes of images and spectra would sit quietly on hard drives, waiting for future scientists to revisit them with better technology. Decades later, someone might analyze that old data with new tools and uncover a detail we missed, a chemical trace, a velocity pattern, a clue about how interstellar bodies travel. In that way, 3IATLAS would keep speaking long after it vanished, its story unfolding across generations of discovery. Meanwhile, nature wouldn't pause to commemorate it. The sun would continue fusing hydrogen, planets would continue circling, and other comets, our local homegrown kind, would continue to streak through the sky, reminding us that our solar system still has its own restless heart. Somewhere in the far reaches of the Milky Way, another interstellar object might already be on its way here, hurtling silently through the dark, unaware of the audience waiting for it. The cosmos doesn't give encores, but it never runs out of performances. There's a humbling lesson in that endless motion. We like to think of the universe as stable, a grand stage set in place since time began. But the truth is, it's a constant flux of creation and destruction. Everything that seems fixed, stars, galaxies, even the atoms that make us, is just passing through. The universe doesn't preserve, it evolves. And in that evolution lies its beauty. 3IATLAS's destruction was not an ending, but a continuation of that endless process of transformation, a small tremor in an infinite, ongoing story. Philosophers and poets would likely find in its tail a metaphor for existence itself. We too are fleeting, stardust coalesced into consciousness, destined to disperse one day, just as it did. Yet, like that interstellar traveler, our brief time in the light can still illuminate the unknown. We observe, we learn, and we leave behind traces, data, art, memory, before fading into the background of cosmic history. The universe moves on, but we are part of that movement, inseparable from it. Perhaps the most striking realization after 3IATLAS's passing would be how interconnected everything truly is. Its atoms, once part of another star system, had crossed unimaginable distances to become part of ours. Now, through its destruction, those same atoms might mingle with solar particles, drift through interplanetary space, or one day fall onto another world. The boundaries between here and there dissolve. Everything in the cosmos is part of one continuous circulation of matter and energy. The universe moves on, yes, but it moves through itself and through us. Years later, when the story of 3IATLAS would be told to new generations, it might sound like a parable of perspective. How a rock from another star reminded humanity of both our smallness and our capacity for wonder. How something so ancient and alien became, for a brief time, part of our shared sky. How its silence taught us that even in chaos and fragmentation, there can be beauty and knowledge. Maybe that's why we look up at all, not because we expect the stars to stay, but because we know they won't. The universe is always changing, always rewriting itself. Every light we see in the night sky is a story mid-sentence, a process in motion. 3IATLAS was just one of those stories, one that happened to intersect with ours for a moment, before continuing on its way. And as the last detectable fragment faded beyond the reach of telescopes, as the data streams went quiet and the world returned to ordinary days, the cosmos would do what it always does, continue. Stars would rise and set, new worlds would form, and perhaps somewhere far away, another fragment from 3IATLAS would glide past another star, unnoticed, except by the laws of physics themselves. The universe doesn't mourn, it transforms. It doesn't remember, but it recycles. And in that vast, indifferent motion, there's something strangely comforting. Because if the universe moves on, so do we. Not as spectators, but as participants, made from the same restless dust. So the story of 3IATLAS wouldn't end with its vanishing. It would end with the realization that endings don't really exist in space. They're just transformations waiting for a new chapter. And somewhere between one star and the next, the universe is already preparing its next surprise. Another spark in the dark. Another reminder that nothing in creation ever truly stops. It only changes form and keeps moving forward, just as it always has.